All right. Semester's winding down. Here's my goal for us. Today we're going to finish the rest of the inductor section, which basically means we're just going to do a bunch of examples today. So hopefully by the end of today, everybody will be a ninja at mutual inductance and at inductors. And I'll be posting a homework assignment tonight, which I'm guessing I'll make due a week from today. But you will have an assignment that will sort of help drill some of the concepts of the inductors for you. The mutual inductors and the transformers. And then hopefully I can get that knocked out today. We'll be done with transformers. And then I'd like to spend the last couple lectures probably doing three-phase circuits, because if any of you decide to get into power, it's good to at least have a flavor of three-phase circuits and kind of like what they do for you and when they're useful and when they're not useful. So we'll probably spend Wednesday and Friday and probably Monday afterwards doing three-phase circuits, and then that'll leave us with next Wednesday, which will be probably just a review for the final. And that's it, we're done.
Wednesday.
Yeah, next Wednesday, yeah. Not this Wednesday.
Yeah.
You have to keep coming after this Wednesday. Okay, just as long as we're on the same page. Okay. Next Wednesday, last day of class.
Chapter 9 and 10 is
Yeah, I mean, right now we're on chapter 10. Right, the final will be chapter 9, which is the steady state power, which we didn't test on. Chapter 10, which will be magnetic inductance, which we're doing now. And to the extent that I can get away with it, chapter 11, which is the three-phase circuits. Again, we'll have yet to see how far we get in chapter 11. What's fun is that if you kind of poke around, we actually did a decent amount of chapter 12 when we were doing the, I don't even think I realized this. I was just kind of poking around this morning through chapter 12 and like, yeah, we actually talked about a lot of this stuff. That's the Bodie plots and the, a lot of the frequency response. I don't really know why they organized the book in this way, but there you go. So we actually made it almost through everything that we talked about. And I think you guys will be in pretty good conditions to suffer through signals with me in the fall. No, this is the fall.
Yeah.
In the spring. Okay, it's been doing this for a while now. They all start to blend together. Okay, so let's pick up where we left off. We were doing inductors, and what I'm going to do is I'm actually just going to work a couple problems from the book because I think they make good examples. That is the most awesome ring ever. I'll bring my glow sticks next time. So I'm going to do exercise 10.9, which I like because it didn't give any, it doesn't actually tell you how to do it. So let me just redraw it so we're all looking at the same thing. We've got a voltage source. I think with some of these problems, the easiest way to explain them is just to do a few examples. 2 ohms. So 2 ohms minus 2J ohms. Then we've got a 1 to 2 ideal transformer. So there's our transformer. And then we've got 2 minus 2J. Actually, this should have been that should be a capacitor. That's bad form on my behalf. Negative impedances are always capacitances. And 2 ohms. All right. And my goal is to solve for I1. Holy moly. Well, what are we going to do? We want to get I1 without panicking. Can anybody make some reasonable suggestions on how to begin? What's the ninja equation that governs all this nonsense? The ideal transformer equation. There we go. Let's start with that. So the equations that govern all of this, first of all, you have to really be mindful of the arrows, and the voltages. So the way I'm going to draw, like sort of the standard notation, is to draw the arrows going into the dots on the transformers. Sometimes in the book, they try to play games and like move the dots. Okay, so there we go. So there's I1 and I2, and we'll call that V1 and V2. And we're going to call this number N1 and this number N2. Those refer to the number of turns on the transformer. All right, and there you go. So what's the equations that govern all this? I1 N1 equals I2 N2, or alternately we could say V1 over N1 equals V2 over N2. So all those things is true. Have I lied? I don't know, I might have lied. It's been like 10 days since we talked about this last, and I was drinking for most of them. I think we're good. Okay, am I any closer to getting I1? Help a guy out. Yes?
V1 over V2 equals N1 over N2?
That is certainly true. So you're saying that V1 over V2 equals N1 over N2? I like that. That's true. I mean, if this is true, that's also true. So that's good. Right, let's write an equation, right? Let's just do what we can do, which is write an equation. So why don't we start with mesh for the left-hand circuit? Okay, I think that's a perfectly reasonable way to start. So, okay, so somebody tell me how to do mesh on the left. Oh, I see why everybody moved. There's a lot of glare. Yeah, I can't. Wow. Okay. Sorry. I'll work my way to the middle, and we'll screw those people over. Okay, so let's do mesh. What do I'll start off. 12 angle 0 equals I1 2 minus 2J. I like it. Is that statement true? No? I think it's true. I mean, that's just Ohm's law. Oh, well, actually, hold on a minute. That's not quite true. There's one missing piece. Plus V1. Now it's true. Yes, sir. You're thinking of mutual inductance. This isn't mutual inductance. It's a transformer. That glare really is bad. I mean, it's like unusually so. I wonder if I pull on these if something... Never mind. Probably set off the fire alarm again. Okay, that's good. I agree. That's the left That's the left circuit. Should we do the right circuit? And we got to be careful to mind our pluses and minuses. So let's kind of work through this together. It's the same. So V2, all right, I'll do the hard part. V2 is it? So clearly it's going to be either plus or minus I2 and then 2 minus 2J plus 2 equals 0, right? The million-dollar question is that a plus or a minus? How can we know? Like, how can we not guess, right? So this is like a common headache, and we got to be able to not guess our way out of this, right? We've got to be able to sort of intuit our way through it. So what's What's the easiest thing I could do? Okay, we always use what's called the passive sign convention. Okay, so they talk about it in the book sometime, right? The passive sign convention, which is just a fancy name for something that you probably already knew. Here's a resistor. Here's a current. So I, R. So if I define I in this direction, where does the plus and minus go on this thing? Plus and minus. Which side has the higher voltage? The top, right? The plus end. So in other words, if I start at the minus end and I go against the arrow, I'm going to increase my voltage by IR. If I start at the plus end and I go with the arrow, I'm going to decrease my voltage by IR. So let's try this over here. I'm going to start at 0. Then I'm going to go up by V2. And now what am I doing? Am I going against the arrow or with the arrow? I'm going against the arrow if I go in this direction. So is that going to increase my voltage or decrease my voltage? According to the passive sign convention, when I go against the arrow, it's going to increase my voltage by I2 times R. So this is a plus. I'm going to increase my voltage. Okay? And it's the same logic applies for all three elements, right? It's because in all three elements I'm going against the arrow. Up, up, up.
What direction is this one?
Well, you can go any direction you want. I mean, I could start here. I mean, so she wants to know, why did I go, if current is drawn counterclockwise, why did I insist on going clockwise? I didn't have to. I could have started here. If I started here and I went up, would I have gone, so let's try it the other way, just so we're on the same page. I think it's a good exercise. If I start here and I go, I cross this resistor, am I going with the arrow or against the arrow? With. So I'm going to decrease my voltage. So it'll be minus I2 times 2 times minus 2J. I'm going to get another IR drop over this one. Okay? And then, when I go over this voltage, is that going to be an increase or a decrease in voltage? I'm going to drop by V2, and then I'll be back where I started. The same equations. It doesn't matter which way you go, as long as you respect the passive sign convention, you're okay. All right, so just erase that. So I've got two equations, and how many unknowns? 4. I1, I2, V1, V2. Right? So, am I any closer to getting an answer? I mean, I am. What am I going to do? How do I fix the 4 unknowns in 2 equations business? Got to make some substitutions. Okay. So shall I get rid of the I's or the V's? How should I proceed? I mean, it'd be nice if the whole thing was left in terms of I1 and I2. Because ultimately I want to solve for I1. Right? If I solve it in terms of V1, that won't be wrong. I will then just have to do an extra step to get from V1 to getting I1, which is a pain.
Can you solve for V2 since you have V1, N1, and N2?
Since I have V1,
No,
sorry.
you don't have V1, N1. I was thinking. I was thinking of 12 angle 0 as V1.
Okay. Right, no. Right. That's not the same V1. Right? 12 angle 0 is not V1.
Use the first equation. We have N1, N2, and then solve for like plug I1 or I2.
Yeah, let's work that a little bit and see what happens. So let's see if we can express V1. Let's see as something. Let's try to get the voltages out of this basically. If we can express this just as currents, then we're good to go. So let's see. According to this equation, V1 is equal to N1 over N2 times what? times V2. Okay, that's a little bit better. That got rid of one unknown. Now can I get rid of V2? I sure can. Wait, can I? Hold on. V1 is N1 over N2 V2. So then I want to say that N1 over N2 is I2 over I1. I2 over I1.
You solve the second measurement for V2 and plug in the I2 into.
So you're saying if I take this equation,
And plug that into V2, you solve that one for V2. That'll give you just currents.
that would give me just currents. Okay, but if I solve this for V2 and sub it in here, then I have V1.
But then you plug V1 to the top equation. And that just gives you all currents across the top equation.
Yeah, but then I'll have one equation and two currents.
You get I1 equal I1.
Can use that one and we have three equations for three unknown.
Three equations for three. There you go. Yeah, I mean, basically we have, that's a good way of looking at it. So Nadia makes a good point that basically, if we include this, essentially now I've got three equations,
One half V2. V1 is one half V2.
and well, I've got three equations and four unknowns.
But if
Right? If I add this equation, then I think I'm good. Right? I can say I2 equals I1 N1 over N2. Now I have four equations and four unknowns. Is there a gentle way of solving this without driving ourselves bananas? I'm serious. I might put one of these on a final. Like, let's let's talk about how we could actually massage this thing into something palatable. I definitely think these equations are right. I think we're okay here. Let's see here. If we took that equation, we could turn that into I1. And we could turn that into V2. Yeah, actually, I think we're okay. Because look, why don't we do this? Why don't we come along and say, we could come to this equation and replace I2 with that. Could I not? Okay, so if I do that, I can take I2 and replace it with I1 N1 over N2. And then I can take this equation, I can take this V1 and replace it with N1 over N2 V2. And now what do I have? Two equations and two unknowns. Okay? So if I do this, I'll get V2, which I may or may not care about, and I1, which I was asked to solve for. And then if I know I1 and V2, I can get the other pair as well. What do you think? Should we solve it? I think we kind of have to, right? I mean, I'm looking at blank stares, and this stuff's not easy. So what would be the easiest way of solving this system of equations? Yeah, with a computer. Okay? In fact, we may do that. But let's just start by writing these equations out and seeing if we can solve them by hand. So I'm going to try to tidy this up just a touch. So what is N1 over N2? Because that expression appears twice. N1 over N2 is a half. Okay, so I think I should be able to come here and replace this with a half. Sorry, I know it's annoying to take notes when I can just erase stuff on the board. But, you know, it's my prerogative. It's actually not that bad. Okay, so it looks like what I've got here is, just to rewrite what I've already got, I've got I1 times 2 minus 2j plus V2 times a half equals 12 angle 0. That's my first equation, just tidied up a little bit. And my second equation is I1 times what? It was 4 minus 2j, but I divided it by 2. So now it's 2 minus j plus V2 times 1 equals 0. And that's pretty cool. Now we just have a system of equations to solve for. And here's the fun part. It's actually not even that bad. I could even solve this one by hand, I think. How could I solve this by hand? How about I double the first equation and do first equation minus second equation? Right? If I double the first equation, this half V2 will just turn into V2. And then I can do top equation minus bottom equation, and I'll be left with one equation and one unknown. So if I do that, so I'm going to do twice this equation minus that equation. So the V2's disappear, and I'm left with I1 times double that, which is 4 minus 4j, minus this, so minus 2 plus j. And what's that going to equal? I really hope we get the answer that's in the book. I didn't work this one at home. Equals what? Double that one, right? Because it's double the first equation minus the second one. So 24 angle 0. So I1 times, what is that? 2 minus 3j. Am I good? Equals 24 angle 0. Therefore, I1 equals 24 angle 0 divided by 2 minus 3j. Hey, does anybody know how to do that division? I'm going to get my calculator out. Seriously, does anybody know how to do that division? I should hope so, because you have a final coming up. Divide the magnitudes, subtract the phases, right? So in order to divide the magnitudes, I need to know what the magnitude is of the denominator. So let's see. So what I've got is 24 angle 0 in the numerator. So let's see. What's the magnitude of the denominator? It's 2 squared plus 3 squared added is 13. So it's root 13. Angle. Now how do I get the angle? Tan inverse of minus 3 over 2. So minus 1.5. And this thing's what, in degrees? So we take tan inverse. And I'm getting about negative 56 degrees. Okay. So putting it all together, if we take 24 divided by root 13, we get 6.65 angle. Somebody please tell me that's the answer in the book.
Yes.
Is it really?
I got it.
Hold on. Ooh! That's not the answer they got in the book. I think they're wrong.
Yeah, but I got the calculator. I used the mattress. I got the same thing.
You got the same as me?
6.65.
Okay, well the only way we could have gotten it wrong is if we set up the system of equations then incorrectly. But I don't think we did. I think we got it just fine. The book makes mistakes all the time. That's what I've learned. Yes?
Why do we have I2 going now?
Why do we have what now?
I2?
Why do we have I2?
The transfer line.
It's the directional current.
Yeah.
Because by the sign convention, we draw the in order to keep everything positive, we put the arrows. Hold on. Hold on. 1018A. Because that's the convention. Current flows into the dot in order to get everything to turn out to be positive. Let's see if I can figure out what we did wrong here. Yes?
I'm not sure if I understand the passive sign convention right, but didn't you say if the current goes from plus to minus, it's a decrease by IR?
Yes.
Why is V2 positive?
Because you think of it like a voltage source. Because it's not in that case, you're not thinking of it as a passive element. You're thinking of it as a source. I think I just figured out what I did wrong. Give me a second here. If I do that, then that turns, hold on a second. If that turns minus, then 4 minus 2j is a minus. So if I now double that and subtract, it'll be 4 minus 4j plus 2 minus j. Sorry, just give me a second. I think we have that's a 5. Let me try that real quick. That may have been the problem. I'm going to look pretty stupid if I got this wrong. Let's see, 2 squared, 5 squared, add, radical, reciprocal, 24 times 4.4. I'm still not getting what's in the back of the book. Weird. Close, but weird. Okay. Okay, I'll tell you what. I think we've worked the problem correctly, but in the event that we haven't, I'll work it out after class, and I will send you a solution just if we're wrong, okay? The book does make mistakes, but I think we've basically solved it correctly, so I'm not going to sweat it too much, okay? If we've solved it incorrectly, I'll fix it for you on Wednesday. Deal? Okay. Okay, so we've got 20 minutes, of which I need to leave you 10 for a quiz, maybe 15 for a quiz. Would you like the whole time for a quiz? No, you're not taking it Wednesday, because we got a bunch of quizzes we have left to give. How to do this. Okay, well, if I give you the quiz in its current form, because I'm giving you 20 minutes. All right, let's do this. I'm going to give you the quiz, but I'm going to modify it, because I am giving you a ton of extra time. So here's how the modification is going to be. And while you do that, I'll figure out what I did wrong. If I did anything wrong, which I doubt it. Mathematically impossible. The quiz says, write but do not solve the equations needed for solving V0. Okay, guess what's going to change now? Write and solve. You need more?
Yeah.
Oh, 2 more? Does anybody still need one? All right, so let's write and solve. Keep in mind, this is mutual inductance, not not a transformer.